G'day everyone. Today we're going to be learning about geometric sequences, specifically the different components of a geometric sequence, what defines a geometric sequence, as well as taking a look at a few examples. So let's get straight into it. So what we have here are three key points related to geometric sequences, but I'm just going to summarize and talk through what it's saying down below. So what it's saying is that a geometric sequence is represented by R, which is a common ratio. Now, how we define a geometric sequence is that we have an initial term A, and the second term will be A times R. The third term would be A times R again. Fourth term will be times another R, and so on and so forth. So an example of a geometric sequence is something like 2, 4, 8, 16, 32, where we are multiplying by 2 to get to the next term. This is an example of a geometric sequence. What I should mention as well is that a geometric sequence may be defined as a geometric progression, or GP for short. If you recall, in our arithmetic sequences lesson, we sometimes refer to arithmetic sequences as APs. Geometric progressions we refer to as GPs. So in terms of what is defining the geometric progression, or the GP, is that we need to have this common ratio. So what defines the common ratio? And that is the division of two consecutive terms. So essentially what they write here. So we have this Tn, which refers to the nth term. And when we divide that by the n minus 1th term, which is just the term immediately before the nth term, we will get this R, this common ratio. So if we take, for instance, we have T1 here, T2, T3, T4. What we see is that T4 over T3 is equal to 16 over 8, which is equal to 2. Alternatively, we see that T3 over T2 is equal to 8 over 4, and that's equal to 2. Or we can say that T2 over T1 is equal to 4 over 2, which is also equal to 2. So we can see that the ratio remains consistent when we are dividing by one term by its previous, by the term that's previous to it. So when we are concerned with the general formula for the nth term, we define it as the nth term being A, which is our first term, multiplied by the ratio raised to the power of raised to the power of n minus 1. So this is the formula for the nth term. And how we get this is, well, we can observe this pattern here, which I'm sort of going to rewrite down below, where we can see the actual formula written over here. So A, and then the next term would be A times R. So imagine we have 2, 4, 8, 16, that pattern. So this would be 2 times 2, and then which would be 4. And then this is A times R, which would be 2 times 2 times 2, and that would be 8, and so on. And so we'd have AR squared, AR cubed, and we can continue. And so if we recall that this is T1, T2, T3, T4, we can see that whatever the n is, we see that the power is 1 less than that. 1 less, and then for the R here, the power is 1, which is 1 less than 2. Now for our first term, T1, a power of the R is 0 because it's 1 less than 1. So if we want, we can write it as R to the power of 0. and we should know that r to the power of 0 is 1, and so we are just left with a. So this is the formula for the nth term, and we're going to be using this to solve questions. So I hope that makes sense, and now we're going to be looking at examples. The first example here says that show that 2 minus 6, 18 minus 54 is a GP, and find its first term a and ratio r. So this is pretty simple. To show that it's a GP, we are going to take the ratio of two successive terms, and we're going to do that twice, because let's say we take t2 over t1 and we say it's minus 6 over 2, because we have t1, t2, t3, t4. That is minus 3. And this is great, you know, we see that it's equal to minus 3, but we don't conclude that it's a GP because we've just divided two different terms together. How we can define that it's a GP or show that it's a GP is if we take another set of two successive terms, divide them, and we get the same ratio. If that occurs, then we can conclude that it's a GP. So we can take T3 over T2, or we can take T4 over T3. Doesn't really matter, but let's just do all three for the sake of it. So that's 18 over minus 6, which again is minus 3. And this is minus 54 over 18, which if we plug it in a calculator, gets us minus 3. So we can see here that because the ratio of these terms are all equal to minus 3, then it's a GP. And what we can conclude is A, which is our first term, is equal to 2, and R is equal to minus 3, which is that ratio we found out. Now for part B says find a formula for the nth term, and hence find T6 and T15. So T6 is the 6th term, and T15 is the 15th term. We know that Tn is equal to A times R to the n minus 1. So we can plug in our values. And that's our formula for the nth term. So T6 is equal to 2 times minus 3 to the power of 6 minus 1, which will be 5. So if I plug that in my calculator, I get minus 486. And T15 will be 2 times minus 3 to the power of 15 minus 1. And that is going to be a very large number. So 9,565,938. So we can see that, you know, this specific GP escalates very quickly, and that will be the case for a lot of GPs. Our next example says for part A, find a formula for the nth term of the geometric sequence 5, 10, 20, and so on. So our ratio will be 10 over 5, which is 2, or we can work it out as 20 over 10, which is also 2. Our A we know to be 5, which is our first term. And so that means the formula for the nth term is 5 times 2 to the n minus 1. Remember, we are following this convention. So that's part A. Now part B says, hence find whether 320 and 720 are terms of this sequence. So to work this out, we need to see if there is a valid n for this equation to work. So it's saying if the nth term is equal to 320, what is the value of n, essentially? And if we get a whole number, then we can conclude that they are terms of the sequence. However, if it is not a whole number and some sort of decimal or a fraction, then it is not on the sequence. And I'll explain that when we sort of solve the question. So I'm going to plug in 320 for Tn and see that it's 5 times 2 to the n minus 1. 320 divided by 5 is 64. Whoops, not 65, it is 64. And what we can do here is log both sides. And when we log both sides, we can bring this power down. And then we can divide by both of the logs. And we will get 6. So this will be ln 64 on ln 2 equals n minus 1. If we plug it in our calculator, we'll get 6. And so that means n is equal to 7. So it's our 7th term. And because n is a whole number, we can say, therefore, 320 is the 7th term of the sequence. That's what we can conclude there. Now, to test whether 720 is a term of the sequence, we will say that 720 is equal to 5 times 2 to the n minus 1. If we divide both sides by 5 first, we get 144 is equal to 2 to the power of n minus 1. Same thing, we log both sides. We bring the power down, which is sort of a step that I skipped in when we were solving this. Divide by both powers. I'm going to plug this in my calculator, ln 144 over ln 2. We don't get a whole number, we get 7.17 to 2 decimal places. And if we add the n, we will get 8.17. So what we've concluded is that if 720 was to be a term of the sequence, it is the 8.17th term. And that is something that just doesn't exist. We can have our first term, our second term, third term, and so on. These are whole numbers. And so they are terms on the sequence. But when we have something that, I guess, is in between these whole numbers, so in between T8 and T9, we will have this T8.17. This is something that doesn't exist. Okay? So what we will say is, therefore, 720 is not a term of the sequence. And that is our question complete. Hope that makes sense. This next example says, find the first term A and the common ratio R of a GP in which the 4th term is 6 and the 7th term is 162. So this is going to be a simultaneous equation question. And so to figure this out, let's get the information and translate that into some sort of equation. So they give us 2 pieces of information. They say the 4th term is 6 and the 7th term is 162. So T4 is equal to 6. And that just means if we use the equation of the nth term of a GP, we get that T4 is equal to A R to the 4 minus 1, or A R to the 3 is equal to 6. And that will be our first equation. And our second equation says that the 7th term, T7, is equal to 162. So A R to the 7 minus 1 equals 162. And we get A R to the power of 6 is equal to 162. And that's our second equation. Now if I take 2 and I divide it by 1, what I will get is AR6 all over AR3. And that's equal to 162 over 6. And what we end up getting is R cubed is equal to 27. And the cubed root of that is 3. So now that we know that R equals 3, we can then substitute into either of our equations, equation 1 or equation 2. And we will be able to figure out A. So let's sub into equation 1. And let's say that A times 3 to the power of 3 is equal to 6. So we get A times, or 27 is equal to 6. And so that means we get A is equal to 6 on 27. But this is a fraction that can be simplified to 2 in 9. So we say therefore A equals 2 in 9 and R equals 3. And that's how we would solve simultaneous equations when dealing with a GP. The final question we're going to take a look at, it says find the value of x if 3x12 form a GP. Now if we recall what defines a GP and how we would prove that something is a GP, is that two sets of successive terms have a common ratio. So if I rewrite the sequence here, 3x and 12, we see that 3 is t1, x is t2, and 12 is t3. Now the common ratio would be t2 over t1, and if it is a GP, this would need to be equal to t3 over t2. Now when we plug in these values, we see that it becomes x over 3 is equal to 12 over x, and what we'll then get is that x squared is equal to 36. And by solving this, by taking the square root on both sides, we get that x is equal to 6, but it can be plus or minus 6, because remember when we take the square root, we can have a negative number because minus 6 all squared gets us positive 36. So what is the answer here? Is it positive 6 or is it negative 6? And the answer to that is it can be both. It can be either. So our answer is x equals 6 or x equals minus 6. Now let's think about it here. Let's say it's positive 6, 3, 6, and 12. What would our ratio be? Our ratio would just be 6 over 3, which is equal to 2. And so our sequence just keeps multiplying by 2. So it'll be 3, 6, 12, 24, 48, and so on. Now in the event that it is 3 minus 6 and 12, our ratio is minus 6 over 3, which is minus 2. And what we'll have here is an alternating sequence where we are constantly alternating between a positive number and a negative number. So if we were to continue the sequence, the numbers would look very familiar to this sequence up here. But what we can see is that because we are constantly multiplying by this factor of minus 2, we are alternating to a negative number on every second term. So to sum it all up, our answer could be either positive 6 or negative 6. They don't give us some sort of restriction on what x can be, so it could be either. And that's our question solved. So that's everything that we have learnt in this lesson about geometric sequences. We went through what defines a geometric sequence, the different components of geometric sequences, as well as the equation for the nth term of a geometric sequence. And we also looked at a few examples. So I hope that all made sense. If you have any questions, do feel free to pop them in the comments and I'll be sure to reply. See you next week.